People often have to analyze images in high-stakes settings. Doctors evaluate scans, content moderators assess photos and videos, pilots respond to fast-changing visual data. In this paper, we develop a machine learning approach to analyze the ways in which people err in doing so. We rely on a unique dataset provided to us by the awesome New York Times interactive team, 16 million human predictions of whether a neighborhood voted for Trump or Biden in the 2020 election, based on Google Street View images presented to readers as part of an interactive experience. This data is cool because it has a large number of human judgments for each image, more than 1,000, plenty to compute a meaningful aggregate judgment, and a ground truth defined independent of human judgment, each precinct's vote share. An independent ground truth is unusual. For example, in radiology, ground truth in datasets is commonly an aggregate of expert opinion on that image itself, not an assessment independent of human judgment. That independence is key here. Without it, studying human error would be circular. We trained a machine learning estimator of the probability that a neighborhood voted Trump given an image of that neighborhood, using tens of thousands of Street View images and the vote share of those neighborhoods' precincts. In our paper, we show that you can get a number of useful results from such an estimator. For example, you can decompose human error into bias, variance, and noise terms, analogous to the classic decomposition for ML classifiers. Noise refers to unavoidable error, that is, accuracy loss due to the intrinsic unpredictability of the outcome from the features of the image itself. Bias is suboptimality in the aggregate human decision, that is, errors in the wisdom of crowds, while variance is suboptimality due to random variation across individual humans. In our data, accuracy loss due to bias is smaller than that due to variance and noise. Humans in aggregate are actually pretty good at this task, thanks to the wisdom of crowds, even though individual humans are erratic and there is a lot of unavoidable error. This decomposition is actionable. If, for example, doctors mainly lose accuracy due to bias, we might retrain them. If they are accurate in aggregate, but individually high variance, we may need second opinions. And if the images themselves are noisy, we may need an alternate diagnostic modality. We also provide several methods for identifying specific image features which lead people astray. In our dataset, one example was pickup trucks. People think they indicate Trump more than they really do, and people also think that visible low-density and high-density environments matter more than they do. Though we discovered these connections independently through our own data analysis, the relationship between trucks and Trump is corroborated by interviews the New York Times conducted with a sample of respondents to their interactive piece. Even if our estimate of the probability that a neighborhood voted Trump given an image of that neighborhood is still imperfect, our approach can still provide useful insights into human error, as long as our machine learning model adds signal beyond human judgment, a property that we verify via logistic regression. You can follow our playbook on other image or non-image datasets with human or algorithmic judgments and an objectively defined ground truth, and these datasets are becoming increasingly available. Here are a few examples from the Nightingale Open Science Initiative, founded by faculty from UC Berkeley and the University of Chicago. This has been Trucks Don't Mean Trump, Diagnosing Human Error in Image Analysis. For details, please see our paper. Thanks for listening.